All right, this is going to be our lecture on the role of linear equations. So some of the basics of linear equations. Most of you should know this, but y equals mx plus b, for m being the slope and b being the y-intercept. So if we have our xy, we can draw some line. This looks close to x equals y, because the slope looks to be about 1 and the y-intercept is 0. So we have y is equal to 1x plus 0, which simplifies to y equals x. So then we can calculate the slope by taking 2 points. So let's say we have a point up here and a point right here. Let's say this point is 4, 4, and this point is 1, 1. I know that's not even close, but it's all right. Then we have y2, so y from the second point, which is 4 minus 4 over, and then x2 minus x1. Sorry, this should be 1. And then we have another 4 minus 1, which gives us 3 over 3 equals 1. So we can also express this as y is equal to f of x. Y is equal to a function of x. And then what we can do is we can also translate it into this form, where we have our ax plus by plus c. This form isn't seen nearly as much because it's really confusing, but you could simplify this equation to give us y equals negative c over b minus a over b x. And that would be the same thing. So then x is the independent variable. So x is something we know, and this will affect our y. So our independent variable will always be on the bottom axis, which is why commonly you see time on the bottom axis, which time, right, if we have some equation, let's just say it's like sine, then obviously sine of t, right, will give us this equation if we say y equals sine of t. And then we can label that as y. So that t will affect y, that x will affect y. So for some line operations, these are some cool things we can do with a line. So if we take the reciprocal of a line, we produce a flipped line over x equals y, which is shown up in this top corner, which basically just, it just flips it. Then we can take our negative reciprocal, which produces the line at exactly 90 degrees from the original line. So if we take this red line as our base equation, let's figure out which one is the reciprocal and which one's the negative reciprocal. So essentially, which one is flipped over our y equals x line? Well, it's got to be the blue one. And then which one's the negative reciprocal? It has to be the green one. And is that correct? Yes, it is. So basically what the reciprocal means is we take our slope of the first line, we multiply it by 1 over itself, and we get 1. So what this means is if we have a line, right, that's going, let's just say it has a slope of 3/2. So our reciprocal line would be the line 2/3, because we take the inverse of it. And now if we take, we want to multiply 3/2 times 2/3, well then we get that equals 1. So then if we take the negative reciprocal, it does the exact same thing, it just makes it negative. So then the slope will be negative, and basically all that does is it flips our reciprocal over our y equals 0 line. So then we move on to linear regressions. What linear regressions do is it allows us to find a good enough line through a series of points. Like if you just have a massive scatter plot, right? And we want to find the best places, or the best line that would give us a correct prediction for x, right? Because then we could predict for this one, this bottom one right here, we could say that, hey, what should y be when x is, let's say this is 10, right? Well, then we just look up the line and we know that, hey, y should be this value. So we can predict things And this becomes very important for like making arms and pick and place systems for FTC, because we only need about 3 data points and then we can accurately estimate every other point on that line. So for the FTC case, this is very, very good for inverse kinematics for joint relations, like I just talked about for a pick and place robot, analog sensors, and encoder ticks. So for inverse kinematics, we have some arm right here, and we know that at this point, we have some relationship between the bottom angle and the top angle, right? And then further down the line, we have that same relationship between the two. So let's go figure out how this works. So this is me a couple years ago figuring this out. It took a while, but I eventually figured it out. I tried to do too much. It's just a linear equation. That's all you got to remember. It's just a linear equation. So in this setup, this was our 5115's center stage robot, right? So we have some distance off the ground to our axis of rotation, which is back in here. And then we have some servo, which I'm just representing as a circle. And then that's it. We have a potentiometer measuring the angle of this socket. So going into more of the math, right? We have our chi right here, our omega, and our theta. Our theta is the rotation from the D line of our arm. So that is measuring, like if it was up here, if we're pointed up, it would be bigger than it is now. This chi is our other angle. If we make a right triangle here, our chi is our other angle from our point. And then we have our omega, which is just going to be our servo angle. So basically, in this case, we're just going to consider that theta should never go past 180. It's normal things that you consider in this case. But then we can derive several things, right? Like if we have any right triangle, that is not a right triangle. If we have any right triangle, we know that the sum of all of their angles is always 180. So then, how can we figure that out? Well, we know that this is 90. And then we know that theta is a given by our potentiometer. And then we know that, our W is going to be this 180 degrees minus chi. Well, how do we find chi? Chi is going to be 90, which comes from 180 minus 90, right? Because we already know we have a right angle there, minus our theta, and then we get chi. So all of this can be solved with a singular value, which gives us that, hey, we have a theta in our bottom axis and an omega in our upwards axis. So there we go. We've found our linear relationship. So then we can see that, hey, if theta shrinks, our chi should get larger and our omega should get smaller. So then the inverse way, if our chi gets smaller, our omega should get really big and our theta should get smaller. Or I guess bigger in this case. But if we make a linear regression for this, we make some kind of tester op mode to manually control our inputs and outputs. So our independent and dependent variables. So like for that arm that we saw earlier, we would say that, hey, servo angle, we need to be able to control. And then our potentiometer angle, I'm just going to put a degree symbol. Our potentiometer angle, we should also be recording. And then we just record our potentiometer into our x's and our servos into our y's. And we plug in our known values. So like if we want our arm, right, to always be flat. Well, if it's up at this angle, that's not a straight line, but you get the point. If it's up at this angle, we want our servo to be at this angle. So then we plug in that, this is what it would be about 60 degrees from where our first location is. So we can say that, oh yeah, it's like 60. And this one is then going to be, what, about 200 probably. And of course, these values aren't going to work for you. It's different for everyone. But then you hop on Desmos and you run this equation, and it will give you your values for your M and your B. And then you can just plug that all in to an equation on your robot, and you're done. It's pretty simple in that sense. So, for how analog sensors work, given an analog output from an axon fourth wire, we can find the position of the servo, which is an absolute servo positioning. So their equation is we take our x, which is our analog output, and we say y is going to be our position around the axis, which is equal to x divided by 3.3, and then we multiply that by 360. This is just what Axon gives you, because that's what it's calibrated to. That's just what they give you. So you can represent this in code, and then you're all good. It's pretty simple in that scenario. So for encoder ticks, how these work is a little bit different, right? Because we know that, hey, if we want to drive a motor, we want to drive at a certain encoder ticks. So our circumference is going to be 2 pi r, and that's just going to be, your normal a circle radius with the radius. And then we take our gear ratio, which is going to be the product of all k's or all n's up to the value k, right? So all this is saying is we have some rev 3-to-1 gearbox, but we're just going to take 1/3. And if we just stack it with a 4-to-1 and a 5-to-1, we have to multiply it by 1/4 and multiply it by 1/5. So it looks difficult. It's really not that bad. So then how these encoders actually work for these linear equations is that we have pulses per revolution, which is always going to be the same. So we can always calculate the distance we've gone based on how many ticks we've passed, because it's always going to be a linear value. You can think of when we drive, right? When we have a circle, and let's just say that circle translates forward, we're drawing a path along the ground where that circle is bent. So our pulses per revolution, or counts per revolution, is just how many times our sensor sees a light, basically. Most use Hall effect sensors, which are just magnets, so they're much more accurate. But the one depicted here is a light sensor. So you can see while it's rotating, it's going to flash that light, and it'll count every time that happens. So then we can derive that, hey, if we multiply our pulses times our gear ratio and divide it by our circumference, we get how many ticks are per inch. And each one of these little bypasses or passes of the yellow light is going to be a tick. So then we can derive a bunch of more equations from this, where our position in degrees is our total pulse count, right, times our pulse count per revolution. Because if we take our total pulse count, it could be like, 1024 or something. And then if we divide that by our pulses per revolution, which is probably only around 38 or 48, and then multiply it by 360, we can get our exact position at any time in degrees. So that's a really cool thing to do. Target ticks is just our gear ratio times our pulses per revolution times the target distance divided by the circumference, because we know that our circumference is how many times the wheel has to turn a full rotation. Then we multiply that by our pulses per revolution, and then multiply that by our gear ratio to find how many ticks, right, that our encoder has to pass. We can also say that, hey, our target ticks is going to be equal to our desired distance times our ticks per inch that we derived on the last one, because it's a simplified way to do that. it makes sense. It helps with our calculations to do it that way. And these are all related to our linear equations because circles, even though they're a circle, when they're laying out a path of where they've traveled, that is a linear equation. So, thank you for watching.